Hello, everybody. Welcome to the Henstitute. I've had a few people ask me about this one since problem 29 actually has a little star by it. They're like, how do I go about solving this? I like this problem because we've got the idea of isotherms in it. We've got isochoric, we've got isobaric situations, all this lovely stuff. And we've got 1 mole of this monatomic gas. It really could be as many moles as we want and it would still work. And you're basically filling in this chart. You're trying to find the change in internal energy, the work, the heat, all that lovely stuff. I'm going to start off with the easiest part. We know during isochoric situations that there's no work being done. So basically from B to C and from D to A, there's no actual work being done. So I'll put in a 0 for that and a 0 for this. The next part is we know from the first law of thermodynamics that the change in internal energy is Q minus W. So in these situations like B to C, if I can find the change in internal energy, I should be able to find the heat and I'll be good. Now, the problem with that is trying to find those different quantities. Well, I have from chapter 14 that the internal energy of a monatomic gas is 3/2 nRT. So if I'm talking about a change in internal energy, I'm talking about a change in temperature. Now this one was nice. They give us the temperature of these different isotherms. So D, for example, is on this bottom isotherm, so it's at 200 Kelvin. C and A are both on the same isotherm, so they're at 400 Kelvin, and B is along this top isotherm, so it's at 800 Kelvin. So when you're trying to find all of these changes in internal energy, you should be able to use this equation to actually find them. So for example, if I was doing B to C, the change in internal energy from B to C, I would take 3/2 times my number of moles, which is 1, times the ideal gas law constant, 8.31, and then my change in temperature. So from B to C, I'm going from 800 Kelvin to 400 Kelvin, so it'd be 400 minus 800. In other words, I am actually decreasing the pressure on this thing. So if I decrease the pressure, that's going to decrease the temperature since they're directly related, and that's going to actually cause a decrease in my internal energy. So I just have to calculate this out, and bam, that's going to be that number, and that's also going to be that number. The hard part isn't so much B to C or D to A, it's how do I do these other ones, these isobaric situations. Well, in an isobaric situation, let's do A to B, for example. We know that the work is going to be equal to the pressure, because it's constant, times the change in volume. And so as I go from A to B, for example, I know I'm increasing the volume, so that's going to be positive work. But from C to D, I'm actually decreasing the volume. This is going to be negative work. But I don't have a good way of actually finding that with this equation because I don't have pressures or volumes on this thing. But if I go back to chapter 14, we know that PV equals nRT. And if I'm talking about a change in my volume, that's caused by a change in temperature. So another way of actually finding the work is to take N, the number of moles, times the ideal gas law constant, times my change in temperature. And I have these temperatures on here, so I should be able to find it. So it looks very similar to the change in internal energy, which is 3/2. This just has N, so there is no number in front. If you want to say it's 2/2 or it's 1, whatever, and that should allow us to find it. And then we know that delta U equals Q minus W. So if you want to, we could actually come up with a relationship between those and combine them together, figure out what Q is, and we've got it. So this is kind of the new stuff. This is kind of the interesting stuff. This is really the reason I think that this problem is a starred problem, because we know this equation, but this is kind of a weird one that we have to use nR delta T to find the work. This one, we've already had, so that one's not that strange, but it's kind of this bottom thing, this idea of finding to work with it. So that's a little bit of help on problem number 29. With that, you've got all the numbers. You should be able to find it out. The biggest thing is the arrows are important. They tell us the sign. You must include the algebraic signs here. So for example, when you go from B to C and you are decreasing the temperature, make sure you're doing 400 minus 800 to get a negative value for that. That means your Q would also be negative. If you are actually increasing your volume, that's going to cause an increase in or positive work. If you're decreasing the volume, that's a negative work. So take those into account and they should help. That's a little bit of help on 29. Hope you enjoyed.